Art Wharton went from an entry-level engineering job all the way to becoming one of the youngest CEOs of a global nuclear engineering company ever. But despite his age, he's become one of the leaders, expanding the business into new areas, and now his company's products are used in nearly half of the nuclear reactors around the world. So I wanted to find out what he thought about the future of nuclear energy, what he thinks is the most genius type of reactor design, if AI was going to revolutionize nuclear power, and the one secret he wishes he knew at the start of his career. But first, I wanted to ask him one thing. What do you think is the biggest challenge of nuclear energy?
If you were to tell somebody that you're going to run a turbine by, setting a campfire, they understand and see fire. But if you tell them you're going to do it with this nuclear reactor that produces a lot of radioactive material, they can't see it. And so there's this air of secrecy around nuclear energy, nuclear technology that makes it very difficult to communicate the benefits and the risks. And risk communication in general, when you're talking about events that are unlikely, makes all the risk communication very, very difficult to bring people in to understand. And many people who I know, especially inside the nuclear energy industry, and myself included, I had a little bit of a fear starting out. But the deeper I learned about how nuclear technology worked, the less fearful I was of it. And that works great for nuclear technologists, but it's very difficult to gain that deeper level of knowledge in the public when there's a million other things that the public really needs to understand about the rest of their lives outside of how electricity is produced.
Public messaging for nuclear energy can struggle to get out because people immediately think of things like Chernobyl or Fukushima, or how to deal with the waste or the cost. And so nuclear ends up having to take a very defensive position by default.
In nuclear energy, the only exciting things that the public has really cared about are the accidents. When your plants are running right, it's a very, very boring activity. The things that really live in people's mind are these accidents, which to a large part taught us that nuclear accidents on those scales aren't as bad as we believed they were going to be before they occurred.
What can nuclear energy do to promote its positive aspects, like carbon emissions or reliability?
This is really where the perspective came for me when I was deciding that I wanted to take an intro to nuclear engineering course. I considered the fact that to live our modern electrified lives with, hospitalization, refrigeration, electrification, the internet, all of these things that I think many of us in Western countries take for granted, there's over 1 billion people in the world who have no access to electricity. And we're talking about how we need to be responsible with our environment and perhaps reduce our impact to the environment. But that is at complete odds with the idea of bringing another 1 billion people out of poverty. So what's the way that you can use the least amount of Earth to produce the most amount of energy? And that's where the fuel density of nuclear energy came in to be very impressive to me. And that's when I realized that if I wanted to have the least amount of impact on the Earth while still living a modern life, nuclear energy was the place that I was going to dedicate a lot of my time, effort, and energy.
That's true. The amount of space needed by a nuclear plant compared to pretty much every other type of energy. Nuclear energy, by being so dense, really provides the kind of scale advantage that's lacking in a lot of other options.
We can talk about the advantage here, but the math of that advantage is so outrageously incomprehensible for the human brain. And so it's really hard to talk about how, the orders of magnitude better in terms of fuel density rather than, 3 times more, 10 times more, which we're used to in a lot of marketing of, say, how we wash our laundry. And they get a more concentrated formula and they say, this is 2 times more effective. And you're like, wow, that's a lot. But fission energy, is orders of magnitude better. And that makes a huge impact on the number of uranium mines that would have to exist at all to power the entire world versus the number of coal mines or lithium mines for all the batteries, for backups, for wind and solar, or all of these things that I don't think a lot of people look at and see.
The hot topic has been small modular reactors, or SMRs. How do you see SMRs fitting into the world today?
The thing that I appreciate about SMRs, and the place where SMRs are going to fit really well, are in areas where either, A, they do have the capital, but they have less capital to invest, and they also know that they're going to get 60 to 80 to maybe even 100 years of benefit out of this plant, but they don't want to do a larger capital investment in a large plant. The other place where this fits better is in more developing grids, developing communities, where putting a 1,000-megawatt plant on a grid in Kenya, for instance, would require a lot of extra grid work to support that amount of electricity. And so starting with 300-megawatt plants that are more akin to what you would find in a lot of smaller coal units, that creates that replacement. Also in communities where they're replacing 300-megawatt coal plants in the Midwest of the United States. So there's a lot of places where this fits, but the economic analysis of small reactors versus large reactors, there are little nuclear engineering details to what the limitations are going to be in the efficient use of fuel in physically smaller core. And that becomes the main challenge of, where do SMRs fit and where do they not fit? So if you have a large developed grid, those larger plants actually perform better financially than, theoretically what would happen in the fuel cycle of a small modular reactor.
What do you think is the most unexpected thing that happened in nuclear energy in the last 10 years?
I think the most unexpected thing to me is that the investment community is actually starting to look at long-term investments. There is a huge amount of both government funding and private equity and venture capital to the tune of, tens of billions of US dollars or tens of billions of euros in developing of new technologies and getting those first projects built. Moving on to advanced reactors without light water as the working fluid really opens up a lot of other operational possibilities for nuclear fission technology. And that surprise is really delightful for me, that there have been those large, whether it be institutional or private investors, that have the patience to understand that they're making investments in generations, not investments in next quarter.
Suddenly, we have a lot of interest from the public in advancing nuclear energy. And that has in turn led to a lot of companies coming up with their own designs, like molten salt, thorium, liquid metal, fast reactors. Do you see the potential for any of these to be actually built?
Absolutely. There's increased interest. Now all of a sudden it's, at least in the United States here, it's easy to talk to my neighbor about nuclear energy because the old thinking has faded there. And there is a little bit of excitement about all these new technologies and what promise comes from it. But there's not a lot of understanding about those new technologies. One of my favorite as a nuclear engineer is any, molten core. Ultimately, the advantage is that the design of those systems uses the uranium resources the most efficiently possible because it's constantly replenishing the uranium and constantly taking away the things that we refer to as poisons into the nuclear reaction. So as a nuclear engineer, that's very impressive. But then when you get to the phase of monitoring what material is where, that's where we get into some elements of accountability that the industry still has to solve in order to realize the promise of that fully efficient molten core that's constantly replenishing. And that becomes very important if you come to understand and appreciate that designing a nuclear energy facility isn't all about energy. There's also non-proliferation concerns. All governments that are really responsible with this want to make sure that we have material accountability so that that material does not get diverted for a bad use. And that's something that's very important to nuclear engineers who may appreciate the elegance of a molten core, but then also need to appreciate the security side of that.
I think that's a very good point, because what I see in a lot of these new designs are things that make engineers very happy, with things like creativity and efficiency, and then they get stuck in the practicalities of having it reviewed by the regulator or proliferation control, or actually getting it to be construction ready.
Yeah. And so there is this sense, and I certainly was that engineer when I was in my 20s, that frustration of, why can't they just let us do the elegant engineering solution here? But there are those practical realities. There's a parallel with buildings. And so an architect can design this really spectacular, fancy building, and it is a complete work of art. But then the constructor comes and looks at those drawings, and that architect is that constructor's biggest nightmare because some of those things the architect didn't consider, is it constructible? They only considered, is it beautiful?
When I was working as an engineer at a plant, if we had a problem with the system, the first group we wanted to talk to was the maintenance group, because they're the ones who dealt with it every day and they knew how it worked. I think there's a lot of hesitation from engineers to talk to people on the ground about what solutions might look like or how the design might be affected.
And that there's a friction there, but I think that friction is also necessary because there can be examples where the person working with that piece of equipment every day is stuck in an old way. So sometimes the elegant engineering solution does create something new, but sometimes it doesn't, and that's why teamwork has become so important in all of these fields.
Can you give a brief rundown of what Studsvik Scandpower is doing in nuclear energy?
With my company, Studsvik Scandpower, which is a wholly owned subsidiary of Studsvik. And at Studsvik Scandpower, we are the software house of Studsvik, and I would even go so far as to say of the nuclear energy industry in the Western world. But our team makes the neutronic simulation software, which is used by nuclear engineers. And those nuclear engineers with our software are designing the reactor cores. They're performing the safety analyses to verify they're going to operate well. And then we have other software that monitors the core as it's operating to verify that it's operating as we intended it to. And then we have more software that tracks all of the spent fuel, all of the production of isotopes, so that we have full isotopic accountability for authorities so that we can say this much radioactive material entered, this reaction occurred, and that much exited. And here's the status at any given time over the next 10,000 years of what that material is going to be. And ultimately, our team writes that software to make sure that the engineers can do that quickly, reliably, and accurately with computers rather than hand calcs, like what was happening back in the 1950s.
I think one of the exciting areas that's coming up is applying machine learning to nuclear energy, where if we have a lot of data available, we can use AI to improve efficiency and reliability.
Yes. In fact, we're actively developing AI tools for nuclear simulation software. And one thing that I think is prevalent in our discussions about AI, especially within the past year, as ChatGPT has really demonstrated to the public the immense power of large language learning models, AI we've had in popular culture, movies and books all telling us about the dangers of letting AI take over. So, I think we're not going to enter the world of the Terminator, where the AI is taking over the world, hopefully. But in much the same way, we, in our software applications at Studsvik Scandpower, are looking at AI to search a larger space of possibilities and then give us an answer. And then from that answer, we use our real physics software and real engineering judgment to verify that that works. And that's only because we know that you can train an AI for a certain space. And then once something is just slightly outside that space, the answer the AI will give is seemingly random. It's not completely, but sometimes it's going to come out the wrong way. And you have to watch out for it. So we're not going to be depending on AI for what we refer to as safety grade functions. So the AI is not going to be in control of the reactor system. The AI is not going to be in control of the control rods or the water chemistry system. But the AI is going to tell us how to predict how those systems will behave so that we can make decisions and calculations off of that.
Ladies and gentlemen, today's video is sponsored by me. But how can I sponsor myself? By giving you something you can't get anywhere else, like taking our most popular product and expanding it into a beautiful spiral-bound notebook. That's right, now your love of thorium is available on paper. So check it out using the link in the description, and the first 50 people will get 20% off. Thank you so much for your support, and now back to the video. If you look back at the last 20 years of your career, what's something you wish you knew before you had started?
Yeah, I've thought about this a few times in my life. It was actually 20 years ago I got my reactor operator license, where that's when the government said it was okay for me to push the buttons on this reactor. There were a lot of things I didn't know walking in, but that drove me to work really hard to try to do more things. And now I'm at the point in my career, where I got promoted into this position when I was 40, which the industry would view to be as objectively young. But if I had known what I know now back then, I'm not sure I would have worked exactly into the same direction. And so I don't necessarily have regrets for not knowing some things along the way and having to grow and having to learn, because ultimately it kept my motivation up to learn, to grow, and get into this place. So maybe, I guess, the only thing I wish I had known is maybe take it easier on myself. Don't be so hard on myself along the way. And that's really it, because every other time I've had to learn something new, I'm glad I learned it. And it's not necessary that I learned it all in the very beginning, because the journey is really rewarding.
What's the one piece of advice you'd give someone who's just starting their career in nuclear energy?
My biggest advice, and I come from the bias of this is really how I work here at my own desk. You're going to have some really great days. You're going to have some really bad days. And maybe I should also say good months and bad months. And you're going to need to really recenter yourself every now and then on why is it that you're doing this? And so I recenter myself on the oath of the Order of the Engineer, making the best use of the Earth's precious wealth and giving of my knowledge for the benefit of humanity. So when I have a really rough week or month, that's what really gets me through to stick it out. And so the recognition that you're sowing the seeds of a tree, the fruit of which you will not eat, really takes a sense of dedication to a purpose of doing something good for the world through nuclear science and technology as we advance humanity and reduce mortality and provide clean energy for the world.
Now, if that's got you inspired, then make sure you watch this video here next to learn the truth about how meltdowns occur and what we can do to stop them.